Hello, I'm Peter Dueben. I'm the leader of Work Package 2 of ESiWACE. We're looking into what we call community tools. So the idea is that we actually take specific partners and we pair them and we work together on a specific topic and generate synergies between the partners, but then also to build tools that actually are useful for the community to run the biggest models we have basically on some of the biggest supercomputers. And we're looking into 3 different topics in particular. One of them is portability, where you look into basically porting the big models to different hardware, in particular GPUs. One of them is numerical precision, where you reduce the precision and then still want to keep the accuracy actually, but then get a speed up as well. And the other one is also performance diagnostics and the understanding how we can actually work with the fastest models in principle. In terms of the portability, we have 2 approaches. One of them is looking into an approach called Cyclone, where you basically port from Fortran code into a different language, and then we can port this language to GPUs, and we get very good results as well already for a NEMO model running a high-resolution system of the Mediterranean Sea. We have another model called FVM, which is a dynamical core that is newly developed at ECMWF, and here we basically port by a GT4Py language, which is basically transforming the code to Python and then onto GPUs. And again, we have made a lot of good progress in the last 2 years, and now being able to actually run the GT4Py FVM version on unstructured grids on the sphere. For reduced numerical precision, we're looking into tools that can basically port a specific code and transform it in the precision level it is working with. And in particular here, there's a tool called Auto RPE from BSc that we're working on. And on the other hand, we're also working on a tool that is basically providing reduced numerical precision for the backend of the domain-specific language GT4Py, and by doing this, we can basically also now natively run specific components of the FEM model on the reduced precision on the real hardware. For the performance tools, we basically have very good results from BSc as well. For example, diagnosis cache misses and also MPI parallelization efficiency. And you can also get information about strong scaling and weak scaling. And finally, we also have a tool called kernel float, where we can now also look into reduced precision studies again and reduce the numerical precision for different parts in the CUDA framework for a specific application. And then also you can make optimizations where you try to find the best optimal precision level for specific parameters in the system. In general, I think the progress is very well. We're doing well in terms of that we achieve our goals and actually also make the tools really useful. I think the next step is also that we want to automate our tools a bit more, that you can also give it to external users more efficiently and so on. But I think we are on a very good track to actually fulfill our plans and ambitions. And I think it's really fun as well to work in this community with all the different partners in a synergetic way.